Welcome to the solution for the AP Atomic and Nuclear Physics problem set number 9. Let's start by highlighting important information here. It says a photon is emitted. That's important. We'll discuss why in a second. As a hydrogen atom. That's important because it tells us the kind of energy level diagram we're looking at. Undergoes a transition from n equals 6 to the n equals 2 state. Calculate the energy, that would be E of the emitted photon, the frequency of the emitted photon, and that would be F, and the wavelength of the emitted photon, and that would of course be lambda. All right, to start off with here, let's take a look at this hydrogen energy level diagram. This is the one provided by the New York State reference table. In AP, they will always have to provide this energy level diagram for you if they want to ask questions about it because they don't provide them on the reference table. So we start off with our electron in the n equals 6 state, and as you learned in the lesson, this electron had to have been excited to the n equals 6 state to be there, and what they of course want to be is back down in the ground state, and they can transition multiple levels to get there eventually. In this particular case, the electron drops to n equals 2 first before going down to the ground state. And when it does that, it ends up emitting a photon that ends up being visible, and we'll see that here in a little bit. And it happens to be the violet photon given off by hydrogen, one of the 4 visible photons that can be seen with a human eye. Okay, so there we have a photon being emitted, and the rule of thumb, of course, is that that photon has an energy that is equal to the energy level transition that the electron underwent. All right, so for A, all we have to do is look at the energy levels for the states transitioned and subtract to get the energy of the photon emitted. Well, it's simply big minus small. If you're not sure what the negatives mean in the energy level diagram, ask in class. But we're going to simply take 3.40 electron volts at n equals 2 and subtract the 0.38 electron volts that it had in n equals 6. That gives us an energy transition, and therefore the energy of our photon to be 3.02 electron volts. For the frequency of the emitted photon, we've learned that E equals HF. We know that our emitted photon has an energy of 3.02 electron volts. And since it's got an energy in units of electron volts, we need to use the electron volt second form of Planck's constant, and of course that would be the 4.14 times 10 to the negative 15 electron volt second form, times F. Calculate, pause if you need to, and we get a frequency of 7.29 times 10 to the 14th hertz. Okay? And we know that that falls in the violet range of visible light. In part C, they want the wavelength. Well, what's the relationship between any information we already have and wavelength? And that, of course, is the fact that it's a photon, which travels the speed of light. So we just have our wave equation here, specific to the speed of light. C equals F lambda. Speed of light, 3 times 10 to the 8th. Our frequency, 7.29 times 10 to the 14th. And solve for the wavelength. And we get 4.11 times 10 to the negative 7 meters. All right, we have everything they've asked for here. More to come on problems involving the Bohr model of the atom in class.